All right, input output. So what I was trying to do today is just kind of like go back to our last class in embedded and attempt to finish the way that input outputs work inside of this microprocessor. So the way that the class is going to go is that I'm going to try to define how these I/O ports are identified, how do you find them, what are they used for, and then after that I'm going to go port by port, showing you the details of each one of those specific little devices, all right? So not every port is made equal. So when you work your software is going to be a little bit different depending on the port you're working. Okay, so each one of these ports is going to have 8 individual circuits. We've known this for a while now. The second part is that every single one of these pins is going to have a multiplex function in it. That means that that circuit could operate as an input-output pin, right? A general purpose input-output, but it could also have alternative behaviors to it. And so what we're going to do today is that we are going to learn how to handle the general purpose digital input-output. So we're going to be only talking about the input-output behavior of these circuits in its digital form, okay? That's the idea behind it. So when it comes to the architectural composition, is how are these systems capable of doing input-output is a combination of 3 individual circuits. One circuit is called the data direction register. That's the kind of like general name that you're going to find across microprocessor platforms. In this processor in particular, they call it the tri-state device, and it's the TRIS circuit. So that's going to be our data direction portion of the circuitry. And then we have the latch. This is called the data latch register. And the data latch registers, they pretty much operate like a power supply. And then we have the port registers. These are the data level registers. And see, these are registers or circuits that give us the ability to actually read information from the outside world. One way to think about them is that they work as a multimeter, right? So it's like a multimeter driven kind of idea, right? Now, the next part for you to remember is that there is a sequence of importance. So I set up the system as a little triangle of importance, all right? And the way that you're going to read this is from the top to the bottom. The tri-state device has higher importance or higher priority before you can use either your port or your latch circuits, right? Does that make sense? And so as you take a look at each one of these ports, we're going to have to study what these little devices are doing. All right, so let's talk about this tri-state device. This tri-state device is a homogeneous read-write circuit. What that means is that every single one of the circuits inside of that register are pretty much carbon copies of each other. They're twin circuits. The circuits do not have any differentiation between them other than its location, its physical location. So for example, even though all those circuits are the same, if you take a look at the A example, so I'm talking now in specific about port A, the circuit connected to A0 is going to physically affect pin 2 out of the microprocessor, right? There is an actual specific physical location of the circuits. So if you take a look at the 7th pin, that's going to be physically affecting pin 13. And so we can actually go to the data sheet and look at all the other circuits and find their pinouts, right? So, but in general terms, what I really want you to understand is that this general purpose input-output do have an actual connection to the outside world, right? Where we can actually see its behavior, okay? All right. So, one of these boxes is a single digital circuit, right? There is only 2 things you can do to that circuit. I can either put a 1 in it, or I can put a 0 in it. All right? If you actually physically put a 1 through software, you're going to make the corresponding port pin a high impedance input. So what we're going to make it is that if you put a 1 on this specific pin, the actual physical pin 2 will become a high impedance input. Now the word high impedance, it should kind of like give you an idea on how your multimeters actually work. And the high impedance is actually a feature of your multimeters so that they don't consume current and change the actual electrical characteristics of what I am attempting to read. Right? Think about it. If I have an electrical system and I connect something to it that draws a lot of current, I am going to change the characteristics of what I am attempting to read. So I'm going to be reading something that is not right. What this means is that microprocessors, when they go into input, in this particular case by taking the tri-state circuit and depositing a 1 in the location that I want to make an input, that is going to make that pin a high impedance input. Does that make sense? All right. If you put a 0 in its place, you're going to make the corresponding port pin an output. All right? So it is your choice. You have the ability to actually manipulate each and every one of those circuits one at a time. Okay? So it looks like this. All right. So let's take a look at how we actually worked. We were working out our software last week. Right? If you remember how we used pointers last week, we were using pointers by taking a pointer and grabbing the address from the data sheet and connecting them, right? So step 1 is what you see right here, right? We're going to take the pointer to a specific port, and then I get its address, and I get the connection done, right? That's what we did last week. We were learning how to use the software tools. Any questions on that? Yes?
I just have a question on what homogeneous is.
Homogeneous means that internally speaking, that circuit is exactly the same as that circuit, which is exactly the same as that circuit. As insofar as when I deposit a 1 in either of those circuits, the behavior that I get out of it is exactly the same. So for example, if I put a 1 in that position inside of this register, that is going to force A0 to behave as an input. So if I take a 1 and I deposit it not on that circuit but on that one, then A1 will behave as an input. They are homogeneous circuits. Regardless of how I interact with them, they will behave exactly the same way.
Okay, the counterexample would be...
The counterexample, I can give it to you once we finish through this. Once I move through it, I'll show you a non-homogeneous circuit.
Okay.
Right? Meaning like I can take a 1 in one position and it makes one behavior, and I take that 1 and I move it to a different spot and it behaves totally different. So we'll show you that. So notice the direction of the arrows, right? When you're working with a tri-state device, software initiates the behavior, all right? So if you notice, you start with the software. When I execute this instruction, I am depositing the hexadecimal number 1, a literal constant, into this location, which is going to force this to happen, right? I'm going to get 0, which is 0, 0, 0, 0, and then the 1, and now you have 0, 0, 0, 1, right? That's what the software is doing, okay? Now, once the software does that, now the circuit is going to behave according to your command, right? And that's what these arrows are telling you. So this is what the software does. This down here is the behavior of your circuit. So here's what happens. When the 1 is deposited inside of that tri-state device, the circuit corresponding to pin 2, it gets configured as an input. It becomes an input. See that? The same thing is happening on that 0. Now, I'm not talking about the guys in the middle because by explaining that 0, we know what the rest of the pins are doing. But the moment that that 0 lands in that position, it's going to force pin 7, which is located in pin 13, right? A7, port A7, which is physical pin 13, will now behave as an output. Right?
All of them wouldn't be an output?
Yep, all of them will be an output. I'm just showing you the corners, and then I'll let you figure out the middle.
Also, you don't have to like set it or warn it. You just gotta say
Correct. You could set an OR if you want to. Let's say that I just want to change the behavior of only that pin. You could use bit masking to avoid changing the behavior of anybody else but the pin that I want. Yes. In this case, because I just want to make sure that I get everybody a startup value, kind of like in your setup. I want to get started somehow. Then I set it up this way. Now, this is totally arbitrary, by the way. It's just totally arbitrary. I chose one because I wanted to show you one as an input and one as an output. Nothing special about it.
And red so that you can see the fourth.
Yeah, I just want you to see that this is because of that and this is because of that number. So that you can actually see the difference between these two, right? You're tracking down what the heck I'm doing here. So that's the idea. All right. So any questions, right? Now, here's what's happening in circuit. Okay? Inside of every GPIO circuit, there is a circuit that is called the data direction circuit. All right? It's something that allows you to change directions into the microprocessor world. Okay? There's something I really want you to pay attention to, and I think it's very, very important for us as we're learning new schematic of symbols. Look at this symbol in particular. It's a square box with an X through it. In the microprocessor world, that means that this is an actual physical post. It's an actual physical pin. I can access it and visually see it. All right? It's telling me that this is physically a position. All right? So when you're reading schematics, and you see that box in your data sheet, if they are telling you this is a position that you can get to. Okay? So think about this data direction circuit, this DDC circuit. By the way, I'll be posting this online. So just want to make sure that you know that this is available. But here's the deal. The deal is this. This circuit has the ability to either draw information from the outside world to the inner circuits of your microprocessor, or you have the ability to draw data from the microprocessor through the direction into the outside world. But if you notice, that cannot happen unless the tri-state is choosing the direction. If a 1 shows up at the input pin, it will work this way. But if a 0 shows up at that pin, then it works that way. It's going out. In versus out, right? The direction of the data flow has changed. Now, here's the fun part. All this fun stuff is to give you an idea of what's happening. If you can get in your mind some sort of a different mechanism by which you understand input versus output, that'll be great. Notice that the tri-state device says nothing about voltage. Nothing. The tri-state device is incapable of handling volts. The only thing it can do is create the conditions necessary to either read or write. See that? Yeah.
So this would be more like me coming from like doing Arduino programming. This would be more like an input. It's reading a signal and
yes.
It's outputting a signal.
Right. Well, let's take from the Arduino world. From the Arduino world, there are some registers called DDR.
Heard of it.
And so the DDR register is what the TRIS register is here.
Okay.
They just changed their names
Okay.
because they're competitors and they don't want to just have the same name. Because I don't know for what reason. It's dumb. They should have called it DDR, but they didn't. They call it TRIS. But that's the data direction, right? It's all about data direction. Now, voltage display happens at a different circuit. And let me show you how that works, okay? So any questions on this? Does it make sense?
I was more wondering if there was more of it's reading high versus low. So like reading a 1 versus a 0.
In this case, this gives you the ability to read.
Okay.
But it's not telling me if I am reading a 1 or a 0. It cannot do it.
Oh.
This one says, yes, you can read. And this one says, I will write.
Okay.
So the micro has the ability to write out, and if I put a 1 in the circuit that I want, that will make that circuit, will give the circuit the ability to read.
Okay.
See that? Because at the end of the day, this box has the ability to read or write, but it cannot do both at the same time.
Okay.
I can sequentially change read then write, but I cannot do it at the same time.
Yeah.
See that? So this says, I want to read. This one says, I want to write.
Yeah.
See it? See the idea behind it?
Mm-hmm.
Okay. Once you have that, it comes the really important part. This is the part that it's usually, you go through all these explanations, and then the question is, how will the problems look like in the test? Like that. All right? So question number 1. Write the C instruction that makes pin D0 an input while the other D pins are output. Okay, so I'll start it. So this guy will be int. I'm making the assumption that this is true. Port D is equal to, I think A is 80, 81, 82, 83. I think this is F83. By the way, you do not need to remember these numbers. These numbers will be provided to you in the exam at all times. You don't have to remember this. In fact, if you remember this, I will just strongly discourage you from trying to remember this. Because in about 18 months, it will become obsolete, and then these numbers will change again. So there is a data sheet for it, okay? So, this should be Tris D, and then somebody give me the number of Tris D.
Was it the 92?
Tris A was 92.
Oh.
So B will be 93, 94, 95.
Yeah.
So Tris D, and then you get the content of Tris D is going to be equal to, port D has 8 elements, and I want D0 as an input, while the other pins are an output. So I will put hex 1. So this is D0 as an input. D1 through D7 as an output. Okay? Can you do C7? Somebody help me out.
Well, still the Tris C, right?
So we're going to go int Tris. If F95 is D, what is C?
94.
F94, very good. All right. It should be there in C. We are trying to get C7 as an input, everybody else output. 0 hex 80, very good. Okay? I want C6, here's problem 3. I want C6 as an output without changing. Now listen to the wording. Look at the wording. This is how watching for the wording is what makes the difference in a test, right? I want you to watch the words carefully. It says, without changing the direction state of other port pins. I want C6 to become an output, but I don't want anybody else to get changed. And that's where bit masking comes to play. See that?
Yeah.
I did not read that carefully. Thank you very much. So if this is changing everything, if you do not want to change the direction, how will it go? So without changing.
Don't you want to toggle that?
Well, assume that this is not done, right? Assume that this is not done,
Yeah.
right? Assume that that's not done. The question is, if I want to make C7 an input, here's the logic that you follow. If I'm going to make C7 an input, I need to put there a 1. Right?
Set it.
So I need to set. Very good. Very good. That's the next logical step. I have to set. What is the gate that I use for setting?
Or.
The OR gate. Very good. So now, the logic is, I'm going to make C7 an input. C7 become an input with a 1. That means that I have to set. That means that I need an OR gate. Right? That's the logic that I'm following to get to the conclusion. So we go. Tres, C, OR gate equals to?
0
Hex 80. Very good. Very good. Still there? Think about it.
Thank you.
Yep, I'll let you think. Let's not move forward until we just get the opportunity to think about this a little bit. So that's important. Make sure that I'm giving you these 3 because the voices in my head are telling me that something like this will show up in the test. All right? So make sure you practice this.
You know, you shouldn't listen to the voices in your head.
I know, but they're like so helpful.
Where is the list of the addresses? Is it in the data sheet?
It's in the data sheet, page 65, and it will be provided in the test. Data sheet is online. If you go to, I think it's called course documents, it should be there. Okay, good. Anything missing in Blackboard, let me know. We just created this automatic deployment system, and chances are that I screwed it up somewhere in there during the semester. So if something is not deploying, please let me know. Could be that.
Deploy in 2020.
I actually did it by action, not by date, because I know I'm going to just do something wrong with the dates. Okay? Okay, let's do problem number 3. In problem number 3, we're going to be writing down the instruction that makes C6 an output without moving anybody else. So I know bit masking is part of the game. Every time you say without affecting somebody else, you know bit masking is part of the way. So I need to make C6 an output. Logically speaking, output is done with a 0. Right? That's what the data sheet tells me about this processor. 0 in bit masking means reset. And reset needs what gate? The AND gate. So we need an AND gate. This means that the shape of my instruction is always the same. It's going to be tris, C, and equals, and then there's a mask that comes in here.
Hex 40.
It could not, because it's a negative mask. You're dead on in the position. Okay, so let me go back. You're right there. You're almost there. So
yeah, it's the backwards. Yeah, it's,
yes. So you got.
I can't remember what it is.
So this is 0, 1, 2, 3, 4, 5, 6. So if you say 40 like this,
Yeah.
this is a positive mask. So if you want to make it a negative mask, you could do the opposite of hexadecimal 40, and that'll work.
Okay.
See that? So this is a positive mask. That made it negative masking. See that? Or you could have simply go, I know it's negative, and I want a 0 there, so then I'll do it this way. That's F,
Yeah.
and this guy is B. So this is hex BF, which is the same as not 40.
So that one's compiler?
Yeah. Hey, David.
Hello.
Make sense? Right? So here are the answers. So you can have your tris D with a hex 1, which is this. You have your tris C, OR gated with a hex 80, which is this. And then there is your tris C ANDed with a BF, which is the opposite of 40. Okay? See that? So during the test and during the quizzes, watch for the without. The moment that they say without, we want some bit masking. All right? Then you try to figure out if I'm supposed to be input versus output, and that tells you if you're going to set or reset. That's the only two options you have, by the way. It's either you set or you reset. Usually, 99.99% of the time, in the same world, nobody will toggle just for the sake of toggling an I/O pin. Usually you want to know the actual state you're going to be in. Because it's not like turning on an LED just by chance. You want to make sure that you know that value. So I have never used a toggle for a tri-state ever in my career. I will never say never because there's always an opportunity down the road to do something crazy. But, make sense? All right. Okay, so tri-state used to determine data direction. That's all we need to remember, right? That's the important part to remember. All right, the second most important register. Notice that if you remember the little triangle that we drew at the beginning, tri-state always happens first, right? In the software world, tri-state always happens first. Now comes Mr. Port, and port is actually quite useful. Port is also homogeneous. Means that every single port behaves exactly the same way given the same set of inputs. Right? Every single circuit behaves exactly the same way given the same set of inputs. That's it. They're homogeneous. They're exactly the same. I'm going to just draw on port A as an example, just for the heck of the argument. So I'm naming every one of those circuits A, A1, A2, A3, A4, all the way to A7, just for the sake of giving it a name. But here's the important part, and here's the part that you have to think about this carefully. Because this is a read-write port, I can read from it and I can write to it. When you write to the port, if you are actually physically attempting to write to the port will send the data to the corresponding lat. Okay? Now, this is important for you to remember. Not every microcontroller can do this. This is an architectural feature of this micro. So one of the first things that you do when you encounter a micro is to see if this feature is available. Either by looking at the data sheet or by simply attempting a write to the port and seeing if the lat responded. You see what I mean? So in some sense, even though I told you that the port is some sort of a reading device, when you write to it, it actually passes the data to the corresponding writing device. Does that make sense? So when you write to the port will send the data to the corresponding latching register, right? That's how this particular circuit was built. And when you read from the port, it actually reveals the status of the physical pin. Now, having said that, this is only true if the tri-state device has been set up properly. Okay? So if you work your tri-state device, if I make my tri-state device an output and I try to read from it, you're not reading anything other than the last value that you latched in. Right? So your tri-state device determines the behavior of the port in some sense. Does that make sense? All right, good. So let's take a look at it. The write operation. Okay, once again, if I am going to be doing a port write, the behavior begins with software. So you start looking at this from this position. Right? You initiate the write. Okay? So the software, in software, I write this number into that register. What that does is that it puts the number 0000, that's the first 0, and then the last 4, 0001. Okay? What the system is doing is that when you write a 0 into the latch, the port sends the 0 to the latch, and the latch sends the 0 through the pin, and you actually experience 0 volts in the outside world for the first time. You can actually take a multimeter and look at it. See that? The same thing is happening with this 1. When the 1 reaches the latch, the latch will actually bypass that and send 5 volts to the pin or the corresponding pin. So your logical one became 5 volts at the outside world. And you can take a multimeter, go to pin 2, hook it into that spot, and you will see 5 volts out. So the tri-state device gives me the ability to send data out, and the port will actually do it. The port is the action. The tri-state is the setup. See that? So the only way that you can do a port right is if your tri-state was set up as an output first. Does that make sense? So, here we go. If you're going to do a port read, then it begins the other way around. You actually begin by manipulating the voltage. Look at the arrows, right? The arrows are moving backwards now. So notice that the action is now physical. This is not a software action. The software action is the trailing end of the entire sequence. So I actually take pin 13. Notice the arrow is looking in. That means that this was set up as an input. Yes?
Does it being equals at the beginning?
No, no equal. Here?
Yeah.
No, no equals. I'll explain that in 1 second. Because we're reading. We're not resetting.
Oh.
See that? Yeah. Very good question, though.
Makes sense now. Okay.
Very good question, though.
Thank you.
But look at the arrow. The arrow means an input. That arrow is telling me that before I was capable of doing any of this, somebody set my pin A7 as an input. So that if you physically put a grounded pin on pin A7, I mean I take a piece of wire, I hook it to 13, and I ground that pin. Like you physically ground it. That will put 0 volts on pin 13. The input buffer will pass that data up into port A, the register. And then, listen to what I'm going to say now, because this is very important. This behavior is non-set up by you. In other words, this is going to happen because it is a circuit. There is no software that I need to do to pass the data all the way to the port. It will happen by itself. The moment that I make my tri-state, this guy, an input, you put 0 volts, and this guy will become a 0. And at any moment when you are ready, if this instruction coincides with this moment in time, I will see that 0 coming through my software. See that? So this software is your choice to do at a specific moment in time. You can say, I want to see what's happening at A7 and at A0. Assuming that it was set up right, what is the instruction that allows me to see it? The answer is that one. Right? I can take this instruction and monitor what's happening there and there. The will take care of the rest. If I put 5 volts on pin A2, on pin 0, meaning pin 2, the 5 volts will go through the buffer into port A, and the 5 volts will become a logical 1. So that when your port instruction gets hit, you actually see that logical 1. So, if you set up your system as a read, 5 volts in the outside world will look like a logical 1 in the port register. See that? So that's the idea. Now, it really doesn't matter how complicated this looks. The reality is this. If I set my trees as an input, when I read it, the system will show me a logical 1 when a 5 is there, or a logical 0 if a ground was there. That's it. It's a very straightforward idea. Make sure that you don't get lost in the little details of how everything else operates. It's a very simple concept. If I make the thing an input, 5 volts will look like a logical 1. If I made it an output, if I make it a 0 volts, it will look like a logical 0. And the port is the one that does it. Okay? All right, so here's the deal. How does this looks in the test? Here's another set of problems that will be very similar to the ones in your test, okay? Let's look at the first one. Notice that I give you a tri-state value. The reason why that is important is because once I give you a tri-state value, input versus output, whoever is an input and whoever is an output is already set. Right? So, I am giving you I'm going tri-state C equals hex 1. What does that mean? The least? So C0 is what? This guy is an input. And 1 through 7, these guys are outputs. That's what that means. Right? Now, check the question. I want you to write the C instruction that sends 5 volts to pin C7 without affecting the voltage on any other pin set up as output. So, the port, you have 7, 6, 5, 4, 3, 2, 1, 0. This guy is an input. These guys are outputs. Okay? I am very much interested in putting 5 volts on 7. So I want 5 volts here. But I don't want to mess with this. I want all these guys to be unaffected. What is the circuit that delivers 5 volts? Yes?
You do OX, or you do
Or.
And OX 80.
Yes, OX 80. What's the circuit that we use for that, though? Port C. Very good. The number one mistake that I tend to see in exams is we tend to miss the difference between a tri-state behavior and a port behavior. Sometimes I ask, can you put 5 volts on the output? And then we use the tri-state to do so. The tri-state can't put 5 volts out. The tri-state can only do input versus output. That's all it can do. It can just handle direction. But if you want to drive voltages, you got to use a different circuit. This is a setup. This has to happen first, and then this has to happen. This is the reason why we drew this as tris, port, and lat, right? The port and the lat are subservient to the tris. The tris has to happen first, okay? All right, here's the next one. Can you write a C instruction that reads the voltage level presented on pin C0, right? First things first. This is making C0 an input, therefore this question makes sense, right? A beautiful question, note, stars, right? A beautiful question would be, write the C instruction that reads the voltage level represented by pin C1. What is that instruction?
Read 0.
Is there an instruction?
No.
Why not?
Because
It's not set up.
Because it's not set up as an input. Whatever instruction I give you will not work. Why? Because my setup is not conducive to an input on C1. It was set up as an output. So I can't read on C1. See? It's a trick question based on the knowledge of circuitry. See that? If I were you, I will put like little stars in your notebook. Right? I'm listening to the voices in my head. You should listen to the voices in my head too. Right? I know the guy that makes the test. So, just saying. Pay attention. All right? Okay, so how do you read pin C0? Well, I'm going to use a read operation. So I'm going to put here read pin C0. So I'm going to take input as the variable that is given to you. A Boolean variable means that it's a single bit variable. It exists in CCS, like the Code Composer Studio has the Boolean data type. It's just a single bit. That's all it is, right? So we're going to do input equals, and then I'm going to use the port C C, and then I'm going to read the least significant bit. Right? See that? Please notice the difference between a read versus a reset. This is a reset. So if you do, this is input, this is a read, you go port C and 1. That's a read. But if I do this, that's a reset. See how it changes? This is a read. This is a reset. Notice that? You know why? Because the AND gate destroys data. I'm going to grab data. I'm going to AND gate it with that. Whatever effect happened, listen to what I'm going to say. Whatever effect happened on this instruction, I am sending it somewhere else. So port C remains unchanged.
It's not saved yet.
It's not saved. I took the data, I took a copy of it, I destroyed it, and then I threw it away. In the next instruction, I grab the data, I mess with it, and then I send it straight back where I got it from. Which means that the previous value gets destroyed. That's the difference between your reset and your read. See that? So that's the difference between your reset and your read. All right, and then finally, I want to write a C instruction that sends 0 volts to pin C6 without affecting the voltage on any other pin set up as output. What is that one? I want to send 0 volts, right? Exactly the same instruction as before, but then our gate. The circuit that we are operating on changes, right? Now, I think that this is the part that I believe is interesting from an exam taking perspective. All right, look at this. This question, write a C instruction that sends 0 volts to pin C6. It's exactly the same question as this one. Write the C instruction that makes pin C6 an output. So if you look at the answer, is circuit N equals BF, right? But notice that the operation is exactly the same as the 5 volt or the 0 volt operation. But the behavior, because we did it on a different circuit, tree C and port B are not homogeneous within themselves. So like port C is homogeneous internally, but not homogeneous with tris C. Why? Because a 0 on position 6 makes it an output. But if I go to the next one, N equals BF on port C, it makes it 0 volts. See how the behavior is different? The operation and the mask is exactly the same. But because the circuit switched, the behavior switches. See that? These problems, you're going to find a whole bunch of this in the test. There's usually close to 25 points. Between 25% to 30% of the exam is in manipulation of these types of circuits. Right? Questions that sounds very similar to this. If I say without affecting, you know that bit masking has to be part of it. If I say something else like, you have to change the entire port, then you know that you use it without bit masking. Any questions so far? Does that make sense? All right, and then finally you get your latch circuit. And the latch circuit, there's not much we need to talk about it because through the port, we're going to have the ability to manipulate the lat. However, if you want to be really accurate, you can actually work the lat directly. It turns out that I have clients that actually, even though some circuits have port forwarding, they actually ask me directly to manipulate the port and the lat separately. for whatever reason. And I think that there's a company in Minneapolis that is called Spartan, and these guys are very, very adamant about manipulating the ports individually. They do not want you to use port forwarding. Apparently, there are certain microprocessors that within the same line, they drop the port forwarding, and then they cannot port their code. And so we have all kinds of interesting requests like that. Anyway, point being now, the lat register is also homogeneous, but notice that this is not a read-write. At least it was, even though it is a read-write, I could read from it. There is actually no benefit in reading from the lat. That is with a little asterisk. There are some minority applications in which we find ourselves reading from the lat, but that's that's conversation for another time. In general, when you write to the lat sends the data to the corresponding processor pin, to the GPIO pin, to the output, straight out. This is to the outside world. And all reading operations shall be done through the port register. All right? So the port register is the one that has a physical connection to the reading mechanism. All right? So in some sense, lat initiates with a piece of software that assumes that your tri-state is an output. So if you put a 0 on the lat, a 0 volt will show up to the output. If you put a 1, 5 volts will go to the output. In other words, we're pretty much redefining what port is doing. We're just not doing anything special other than saying, if you do it through the port, you'll be fine. So here's the important part. For this processor, for the processor we're using right now, port write operations are forwarded to the lat. And therefore, all the operations that we're going to be doing in this class from now forward, you're going to notice that I will do all my outputs through the port, not through the lat. That's all there is to it. Right? It makes it a little easier to do read-write through the same register. Okay? Any questions? So there it is. These are the three major ideas behind the port, the tris, and the lat. Okay? So now, software considerations. Here's the part that I really wanted you to pay attention. Oh, you were copying. I'm so sorry. You have something else you want to copy? You good? You're good? Okay. My bad. If I'm going too quick, please let me know. Okay, so here's the deal. I'm going to take every port, one port at a time. I want to make sure that every single port is covered in its own, because these ports are not the same, right? They're absolutely not the same. So let's talk about port A. Port A in particular has a higher layer above and beyond the tri-state, because the tris, the port, and the lat are inherently digital circuits. The problem is that port A could also be analog. And so there is a higher layer that you have to worry about before we can move on to something else. And so that is the digital versus analog control or behavior of a specific GPIO pin. Okay? So what this means is that you got to follow the sequence, right? You got to have the analog control taken care first so that the tri-state makes sense. And you cannot mess with the port unless the tri-state has been set up properly. See that? So what's going to happen in software, the reason why I call these software considerations, is that you're going to have 3 instructions to manipulate one pin. You're going to have to control the AD con first, control the tris, use the port. And it has to follow this sequence. Okay? Without that sequence, it will not work. At least it will not make any sense. Any questions? All right. So here it is. Here is the pinout. In green, you see the nomenclature for digital pins in the microchip world. So microchip calls anything RA, RB, RC, RD, RE a digital I/O. That is the GPIO, general purpose input-output. However, notice that they are not in sequence. You're going to have A0, A1, A2, 3, 4, 5, and there is 6 and 7 actually split on pins 13 and 14. See that? But I want you to notice that multiplexed in the same physical pin, there is more hidden behaviors. And every behavior is a circuit, by the way. So you have a digital circuit and an analog circuit in the same pin. See that? It turns out that by default, you could make this processor come up all digital or all analog. When you buy the system, most of these pins, all of these pins, will actually naturally boot up as an analog pin. So before you can use the tri-state, like we were talking about here, before I can use the tri-state, I have to take control of this digital versus analog behavior. See that? So on port A, this has to happen. I have to control the A to D before I can go into my digital stuff. See that? So how do we do that? The registered ADCON1 exists in chapter 19. Okay? That register contains the bits that are necessary for the behavior of port A. Okay? So I'm going to go back to this. If you notice port A, I have AN0, AN1, 2, 3, and 4 as part of port A. Notice that AN5, 6, and 7 are not in port A. They're on port E. See that? So we just have to contend. It doesn't make any logical sense now, but this is what they did, and we just have to follow what they did. So what they did is the following. If you want to use A0 as a digital pin, one of the things that you have to do is make sure that the analog version of it is not active. Because it has to be either digital or analog, but not both. Make sense? Now, the ADCON1 control register, that register is the one that decides the behavior of that pin. So here's how it works. On the low end of the ADCON world, you're going to have these 4 circuits that together, the 4 circuits together are the control bits. Notice that it says bit 3 through 0 is one port configuration control bit. See that? That makes sense? So here's how you read this. You have on the top, I put here a little blue box so you can see it, AN0, 1, 2, 3, 4, and 5. See that? 0 through 5. See them? And you can actually look at them here. 0, 1, 2, 3, 4, and there is 5 here. I shouldn't have control 5, but it's only 4. All right, so let me go back to it. So there is 0, 1, 2, 3, and 4. So here's what it means. Check this out. If I put 0, 0, 0, 0 in these 4 circuits, ports 4 through 0 are all analog. See that? So this is the software value that will make this circuit behave that way. So if I want to make AN4 digital, right here, 4 is digital, but the rest are analog, you have to put there hexadecimal B. See that? You just have to read the table. Just read the table. Now check this out. If I put 1, 1, 1, 1 here, if I put 1, 1, 1, 1, every single analog circuit will actually be configured as a digital pin. See that? Does that make sense? So, if you want 1, 2, 3, and 0, 1, 2, 3, and 4 to be digital, all of them, you're going to have to put an F in here. You see that?
So this was chapter 19.
Yeah, this is chapter 19. It's in register 19-2. It's called ADCON 1. All right? All right. So here we go. Here's the software. So I'm going to be going back and forth. I want you to see a couple of things. Number one. When you take a look at this bit masking this bit creation up here, this is nothing more than I want to create a bit connection to my circuits. So I have the Tris A circuit, the port A circuit, and the ADCON circuit. Right? This is the part that's green. Then I go with the Tris. Then you go with the port. Right? I'm just creating a connection. This is last week stuff, right? Okay. Once the connection is made, This is the recipe. And it always works the same way. Okay? What you're going to notice is that 90% of the work that you do in a microprocessor is proper setup. And the setup is a recipe. Yeah, go ahead.
You also set up the lat too?
No.
No.
Because the port forwards everything to the lat. So then I don't need to worry about the lat.
Okay.
All right? So here we go. Step 1. Create and connect your pointers. So that's here. Step 2. Configure the GPIO as digital. And this is for port A because port A could be analog or digital. And that's done right here. ADCON1 OR gated with a hexadecimal F. That will make all GPIO pins digital. Right? Let's look at it again. Look. If I put an F in these pins, I got 1, 1, 1, 1. That means that every single pin in the microprocessor goes to digital, including the 5 guys in A. See that? Here's the problem with this micro. This micro does not give you individual digital control. It is sequential digital control. So if I want IA and 1 to be digital, you have to make 0 digital too. See it? Because if you choose the other way around, sorry. If I make 0 digital, you got to choose everybody else to be digital with it. There is no way, there is no setup in which I can have 0 digital and everybody else analog. See that? So what it tends to happen in circuits like this, we start allowing systems to become analog from the most to the least. So we start using them up here because I can have that digital and all these analog, and I can have these 2 digital and all those analogs, and so on and so forth. Does that make sense? In other words, you cannot pick one and all the other ones not. They got to be just together. Does that make sense? Maybe there's a better way to explain that, but that's the idea. Okay? All right. So here we go. Make it digital, make it output, force an output. See the sequence? I actually make it a digital bit, then I make it an output, then I write voltages in it. So that's the sequence that you have to follow. See that? If you're going to do an input, digital input, same thing. Look, this is digital input. The recipe, the same. Create a connection to pointers, configure the GPIO as digital, configure the digital GPIO as input, and then read the desired pin. So it goes like that. It goes, make it digital, make it input, read it. See that? So if you really think about this, the knowledge of the circuit gives you the sequence, and your knowledge of the software gives you the nomenclature that you need in C language. Does that make sense? All right. So this is nothing more than a reminder. So you can actually take something like this and bring it to the test. So you can use it as your reminder. Somebody says, read an input from port A, or somebody says there is a switch connected to port A0. Oh, there's a switch connected to port A0. That means there's an input, so I need to connect all the necessary pointers, make the pin a digital pin, set up the tri-state as an input, read. Right? It's kind of like a reminder. This is nothing more than a recipe that I'm going to follow to get everything set. Right? Every circuit has a setup recipe. And by the time that you get old and gray, you will remember them from the top of your head. Not because you're smart, but because you've done it like a billion times. All right? So, port B, and now we're going to start catching speed. Okay? Port B, same thing. Port B contains a whole bunch of analog stuff. Let me show you. Here's port B. Port B is on the top pins from 33 to 40. Here's the Bs. They're all together. But look at the As. Some of them have analog in it. So analog 8, 9, 10, 11, and 12 are located inside of port B. See that? So if you want to use B2 as an input, digital, you're going to have to shut down the analog version of it. And so that's why we go in here. So you have 8, 9, 10, 11, 12. Those are on port B, while 0 through 4 on port A. So you got port A has some analog, and then port B have a bunch of those too. So, right? Does that make sense? So now that means that if you're going to do some sort of a output on port B, you also have to do digital output right to it. Right? The formula for port A and port B is exactly the same. See that? Any questions on this? Input is the same. Digital input followed by read. It's always the same. One thing that you have to remember is this. This compiler in particular, or most of the low-end compilers will actually force you to actually create your variables right there at the top. If you don't, it actually gives you some sort of a expected, I think the error reads like expected identifier at this spot or something like that. There is an expected identifier. And it only means like make sure that you declare all your variables on the first line. Don't do it after you begin executing, or the compiler will just bark at you. Okay, so that's the recipe, exactly the same as port B. Something interesting about port B, and I think this is very, very, very important for you to remember. Port B is the only port that contains internal pull-up resistors in it. All right, and these internal pull-up resistors are very useful when you're doing input interfacing. And we're going to talk a little bit about input interfacing later. Let's just do it right now so that we can get it out of the way. It's easier this way. So what I mean by input interfacing is that I think we've done this in embedded. So if you're going to interface with a microprocessor, so if I do a switch interface, so if we do a switch interface, we usually have the switch like that. We got a switch, a connection to the micro. So I'm going to put here the little micro connection, right? And then we got power in one end, and then we got a pull down resistor on the other, like so. Right? And this gives me a press with a logical 1, and then a release gives me a logical 0, right? You can also have it this way. You can have the switch, connection to the micro, and then you have a pull up resistor to power, and then you have this grounded, and then it just simply changes the behavior. This is a press, gives me a logical 0, and a release will give me a logical 1. Okay? Yes. It's telling me that you guys should be getting out of here soon. Okay, so that means that if you are making a connection on port A, right? If I'm making a connection between a push button and port A, that's the kind of circuit that I can actually utilize. Okay? Does that make sense? I'm going to say that again. If I ask you to connect a push button on port A, that's how you have to do it. However, if you have pull-up resistors available, like in port B, if the pull-up resistors are engaged, that means that I can connect my circuit by simply taking a switch and grounding it. Like that. Okay? Why is that? It's because internally, the port B line, this port B line, that port B line is being pulled up to 5 volts internally. Okay? So that means that I don't have to force the pull-up resistor internally. Externally. It's already been done inside of the micro. So you can think that inside of the microprocessor, inside of the micro, they did this. See that? Why is this useful? Well, if I save incredibly in parts. If I have 2 push buttons and I'm pumping out 10 million units, it makes sense right away. It's way less parts, it's simple to manipulate, and so I know already that I have my pull-up resistors. Now, here's the catch. The catch is this. There is a single bit that controls the entire pull-up. So that means that when that bit goes to 0, which is active when I put a 0, right? It's active with a 0. When I activate the pull-up resistors, all pull-up resistors go up. You cannot control one at a time. Either the entire port gets pull-up resistors or none of them get pull-up resistors. So single bit control for 8 circuits. So no individual control available. The other part is that the moment, let's say that you engage the pull-up resistors and then you make one of the pins an output. This is a great question for an exam, by the way. This is always a great question for a test. It's actually right there in the data sheet, but we don't like to read it sometimes. So here's the deal. If you make the pin an output and at the same time you have pull-up resistors, the pull-up resistor gets disengaged. It actually gets turned off. So even though there is no individual pull-up control, in some sense there is. Now, the consequence of this is that if you do not press the push button, and I take an oscilloscope and I sneak it in here, when nothing is pressed, you will read 5 volts. That's the consequence of it. The logic is going to flip on you. Does that make sense? This is really useful when you have keypads. If you're going to be using a keypad, you use pull-up resistors so that you avoid putting a whole bunch of resistors outside of the microprocessor. All right? All right, so that's it. Only port B has them in this circuit. Other circuits have it in every port. This guy only has it on port B. You cannot find them anywhere else. All right? Okay, good. Now we're flying. Port C. Port C does not contain any analog pin, so it's a piece of cake. Here's port C. It's split between the left and the right side of the micro. There is absolutely no analog ports in it. So, the configuration as the digital is not needed. So notice that the circuit is exactly the same, but the AD con disappeared. See that? The AD con is not necessary for port C. See that? Any questions on this? No AD con 1. You don't need it. Port D, that is the recipe. Only 3 steps. Set up the pointers, make it input versus output, and then whatever you want to do with it, right? And here is port D, no analog. Port D is actually split here and there. So if you notice, those guys have no analog. So same thing, same circuit. See it? All the same. Port E, that needs analog. See that? Look at port E. Port E contains analog 5, 6, and 7, right? So port E also contains an analog circuit in it. So we have to worry about it. So there is the port E right here in the middle. See that? So then the circuit goes back to the original recipe. Now you have 4 steps. That's it. Nothing special. All right, so I'm just going to bypass all that. So I'm going to leave it here. You got 5 ports. Port A, B, C, D, and E. The pin count on port A, B, C, and D are 8. Port E is only 3. And you have analog and digital everywhere except port C and D that are fully digital. Right? Any questions on that? Kind of like straightforward. Yeah?
Didn't we start the lecture with you saying there's 40 GPIO?
It's a 40 pin 32 GPIO.
Oh, okay.
Yeah. Okay, so here's the fun part. All right. The question is, what can we do with this? Okay? And so we can create an application in which we have an LED matrix. Let's make it monochromatic at the beginning. So monochromatic means just one color, right? So one color. Imagine that I'm just going to make a 4x4 matrix. I don't want to make something really big. I actually built last year an 8x8x8. I don't want to build an 8x8x8 ever again. Ever. If you, yes, but if I ever do, I'll buy the kit online already and already soldered by somebody else. So I thought it was going to be fun until I was the one soldering the box. And then I realized that I don't want to do it. If somebody asks me, how do you do it? I will tell you, don't do it. It's that bad. And if you want to do a box, I'll definitely tell you, do a 4x4x4 because you're going to hate soldering by the time you're done with the 8x8x8. It's beautiful once you turn it on and you program it, but other than that, not fun. Okay, so 4x4, one dimension. Okay, 2 dimensions, sorry. Check out how we're going to be connecting these guys. We have our rows are going to be our anodes, and so you're going to have one wire that goes through all the anodes of every one of the LEDs that belong to that row. And the column is going to actually have the connection of all the cathodes in that row, in that column. Okay, so I'm going to just name them. The rows are going to be letters, and then the columns are going to be numbers. Right? Just, it's kind of like, pick one. All right, here's the deal. Let's just name them. We're going to name these guys. So I'm going to call this guy A1, and then A2, A3, A4, B1, B2, B3, B4, and so on and so forth. Right? Makes kind of like sense. Okay? All right, here's the deal. We're just going to try to figure out how do we make some basic shapes appear in this matrix. Okay? So, if I'm going to make this shape appear in this matrix, I can have these 4 electrical states. One, with a bar, when you see a bar in that little box, it means that I am physically disconnected from it. You can disconnect with, I don't know, you can take a transistor. You take a transistor and cut it off, and then the transistor shuts down all current to that spot. No current flow. Right? So we could use a transistor to just completely disconnect the line. So I'm going to call this physically disconnected. And then you have 0 and 1. That's your electrically grounded and electrically powered states. And then I have X. X means that the voltage level really does not matter. I don't care what you put in that voltage level. It really doesn't matter in the overall behavior of the LEDs. Okay? All right. So here we go. This is how the all-off state looks like. So, my columns are my common cathodes. So if I disconnect all the cathodes, maybe I just have 1, 2, 3, 4 transistors, and I take those transistors and I cut them off, right? I just electrically just make sure that they're in shut-off mode. I will have no current flow regardless of the voltage on the road, right? So by disconnecting these 4 guys, I automatically create an all-off condition. Right? Does that make sense? All right. So what about making one row? So if you're going to turn on one full row, the only thing you need to do is that you take all the columns and you ground them. Okay? And then I put 5 volts in the spots that I want the current to flow through, like so, right? So I have this flow, and then this guy has that flow, and so on and so forth. And then I put zeros in the ones that I do not want on. Right? Pretty straightforward. You see that idea? It's pretty easy. What about columns? Here's columns. In columns, I just take all my rows and I power them, and I physically disconnect the ones that I do not want to turn on, right? And then I take the one that I want to turn on and I put a 0 on it. And then I get this entire guy to turn on. Does that make sense? You better make sense because you're going to be doing this pretty soon. All right? Now here comes the last one. The last one is a single bit. So for a single bit, I have to match the ones that I want off with the zero. So I have to have zeros were the ones I do not want on, and then I have a 0 as my ground, and then I got 5 volts in the one that I want to put on. And this sounds great. This is fantastic. Let me ask you a question. What if the pattern that I want is neither a row, nor a column, nor a single LED? What if the pattern that I want is the 4 corners on? What do? And here comes biology. Right? I have to figure out a way to do this so fast that your eyes cannot see that the LED actually went off. Because how in the world, electrically, you're going to give me this guy and that guy on at the same time? How do you do it? Should be elemental now. How do you do it? How do you turn this and this at the same time? Well, I could do something else. What happens if I put a 0 here? It turns that one on, right? What about patterns? What if I want to make this for this, and that? You do 5, 5, 0, 0, right?
Yeah.
What if I want to make a line? What if I want to make that line just rotate? So, all kinds of interesting questions like, what about sequence? What about permanence? What about update rates? What about multiple patterns? And that's the setup. That's the setup for lab number 2. So here's what we're going to try to do with lab 2. We're going to take a micro. We're going to grab a 4x4 matrix. Right? We're going to start in a simulator first, and then we're going to move it to a hardware. Hopefully, all the hardware will come in on time, and we're going to be able to actually do it on the bench. So we're going to take this 4x4, and then we're going to try to just create as many patterns as we could possibly put on them. All right? So I'm going to just put simple patterns at the beginning, and then I'm just going to then let you guys choose a pattern of your choice after that. Right? So we're going to make it so that you have columns show up. You can make it rows come up and down. We can make it the diagonals coming in diagonals. You can actually make it rotate, and so on and so forth. Right? Then we're going to add colors to it. So instead of having only one color, we put an RGB on it, and then we just make it multicolor. And see how we go about doing a multicolor system. All right? So that's the idea. That's where we're going for the first challenge. All right? That's the first thing we're going to try to do. So anyway, we're done.